Hello, my name is David Scher. I'm back for another lecture in Physics 572, Introduction to Health Physics. My last video discussed internal dosimetry and the basic science that's used to calculate internal doses given an intake. And so now we're going to talk about how that applies in occupational dosimetry. So in the workplace, how do we assess doses for workers who might be exposed? So here I'm going to share my screen with you, and we can move on to the topic. Okay. So as I said last time, we talked about dose coefficients and all the information that goes into developing those dose coefficients. We know about the biology of how, the kinetics of how different chemicals that may be radiolabeled move throughout the body, and what organs they accumulate in, and how the compartment models are used to estimate the retention times. And then we have the activity curves in individual organs, and how organs irradiate neighboring organs, and how this produces a dose that we can calculate. We know that this resulted in a table, a set of numbers that correlate a given intake to the effective dose equivalent, or the organ dose. And we talked about that the effective dose is going to be the intake times the dose coefficient that's in those tables. I showed you one source of information, Federal Guidance Report number 11. It shows a number of coefficients. Other tables exist. ICRP reports in recent years have used updated tissue weighting factors, updated radiation weighting factors to provide new tables, and those are they're out there. But for most of us, we work in a world regulated by the Nuclear Regulatory Commission, and in that environment, we need to use the numbers that are in FGR11, because that's the basis for the regulations. Now, given that we have these dose conversion factors, those coefficients, we can take that. So that information tells us that the intake, we know that the dose is equal to intake times the dose coefficient. We can reverse that. We can invert that calculation, and we can find out that, that what the intake would be that would be equivalent to some dose. Suppose we're interested in a dose of 1 sievert. We can use the dose coefficients to tell us what the intake corresponding to that is. How many becquerel would produce 1 sievert of dose? So we could build a table of becquerel. If we use the annual limit in the regulations for the effective dose that we're interested in, then the numbers, the intakes that occur as a result of that, would be the annual limit on intake. A worker can receive no more than this activity in order to have their effective dose be less than the standard. And so these tables exist in the regulations. An intake of 1 alley produces a committed effective dose equivalent that's equal to the corresponding annual limit. So that's true for organs that generally distribute throughout the body. If a nuclide or a particular material concentrates in an organ, then you can have an alley value that would correspond to the annual limit for an individual organ. The limit for dose to individual organs is 50 rem a year. The effective dose equivalent for the whole body is 5 rem per year. And so you can have annual limits that correspond to both those standards. And so these alleys have been published in federal regulations. And for the U.S. NRC regulations, they're located in Title 10 of the Code of Federal Regulations, Part 20, Appendix B. And so I'm giving you a link here that you can find these tables, and we're going to show you what these tables look like in the next few slides. Okay, so this is the information that is used for assessing doses in an occupational setting to ensure compliance with the limits. So if you go to this link, This is the page you would land on. It is Appendix B to Part 20. This particular page gives a lot of description about how these annual limits for intake have been calculated, what assumptions are present in them, etc. A lot of the information that I presented in my lecture will be reflected here as well. In addition, you click on this link for the list of radionuclides, and you come up with a table that shows many nuclides and what the corresponding limit alley would be. So that doesn't show the alley. It shows a list of nuclides. So let me see if I can give you an example. So pick a different browser. So here we are. If I click on the link that says list of nuclides, this is what I get. All kinds of nuclides, many nuclides. If I pick a particular nuclide, then it will give me information. So let me just pick one just to illustrate for you. Let's go with molybdenum 99. Then it will give me a table that looks like this. And so now we're going to unpack this table so you can understand how to interpret it. Here's an example using cesium-137. And this class shows the alley for cesium-137. For column 1, this is the limits for workers. This is the alley for oral ingestion. So if a worker, and then 1E2 is 100, so if a worker has an intake of 100 microcuries, that would be equivalent to an effective dose equivalent, a committed effective dose equivalent of 5 rem. And column 2 shows the patient, a worker who receives an intake of 200 microcuries will have a committed effective dose equivalent of 5 rem if it's by the airborne inhalation pathway. So that's how we read these tables. We find the nuclide that we're interested in. Then we can look up what we know our pathway of exposure, whether it's oral or whether it's inhalation. And then we can find out what would be the intake that would correspond to the annual limit. Now notice that the cesium-137 entries reflect only stochastic limits. And there are ways to see this. Cesium is a salt. It's like sodium. It distributes throughout the entire body. It doesn't concentrate in a particular organ or tissue. But that's not true of all elements. Some elements do concentrate in a particular organ or tissue. And so iodine-131 is one example of one that concentrates. It does concentrate in the thyroid. And so the dose, let me move these things, the dose, when iodine-131 is either ingested or inhaled, the dose to the thyroid will reach 50 rem to the thyroid faster than the whole, at a lower activity than the whole body would receive 5 rem committed effective dose equivalent. So column 1 is the oral ingestion. Notice that there's 2 entries. One tells me the organ, it's 30 microcuries, is the thyroid limit. And also below that, it's got a number in parentheses. This is the stochastic limit that applies to effective dose equivalent. 90 microcuries will reach the limit for the effective dose equivalent. So 30 microcuries will reach the body limit, the thyroid limit of 50 rem. 90 microcuries will reach the whole body limit, effective dose equivalent of 5 rem. Now, column 2, this is for inhalation. We have the same situation. The inhaled activity will concentrate in the thyroid, and we have 50 microcuries inhaled activity, total intake, will result in 50 rem to the thyroid, and inhaled activity of 200 microcuries would result in a committed effective dose equivalent to the body of 5 rem. Now, also in here is a column that says DAC. DAC is the derived air concentration. So we know what the intake by inhalation needs to be. That corresponds to the limit. We can then assume a standard breathing rate and a standard air intake rate, and use that to calculate what the concentration would be that would result in the intake that's equal to the alley. So the standard respiration rate is 20 liters per minute, and the exposure time that's assumed is 2,000 hours per year. So that's 50 weeks working at 40 hours a week. That's how we get the 2,000 hours. So if you do this calculation, I have it here. So for item 131, the thyroid limit is 50 microcuries per year. If someone takes in 50 microcuries during a year, they reach the limit. Now we have 2,000 hours per year, and we have 20 liters per minute. That's 2,000 milliliters per minute, and 60 minutes per hour. This should be hour. I'll have to fix that in the slides. 60 minutes per hour. This gives you a concentration of 2 times 10 to the minus 8 microcuries per ml is going to lead to the same dose as microcuries per year would. So this is what we call the derived air concentration, and it's this is how much air concentration a worker working in for a full-time job would produce the annual limit. So if we go back, you can see that it reports the same concentration right here. That's the DAC. It's only reported for this alley. If we need to calculate the committed effective dose equivalent based on concentration, we can do that by looking at the ratios of the alleys. This alley produces a dose of 50 microcuries. So if we consider that this activity would produce a dose of 5 rem per unit, we can use ratios and proportions to equate those. Okay. So in a work environment, it's often easier to make decisions based on airborne concentrations in the environment than on some intake value that a worker might receive. We measure the air concentrations directly, and so it's relatively easy to make decisions based on airborne concentrations or DACs rather than having to think about the activity, because the activity is going to be dependent on how much time the intake is going to depend on how much time the worker is in the facility, etc. And so if I'm going to now show you the relationship between the DACs and the alleys. If the total intake is known, then the dose is the intake times the limit divided by the alley. So if you know that a person has an intake of 10 microcuries, then their dose is intake they have times the 50 rem for the thyroid divided by the alley. And for stochastic exposures, it's the dose is the C. The dose is the C. Committed effective dose equivalent is what we'd use, and the limit in that case would be 5 rem. If we're talking about organ doses for non-stochastic standard, then the dose is the tissue dose of that organ, and the limit in this calculation is 50 rem per year. Alleys are shown in the table. Now, the dose due to airborne activity is proportional to the concentration and to the exposure time. So we can use a new dosimetric measure. We can talk about the exposure a person receives in terms of DAC hours. So the DAC hours are the concentration the person's actually exposed to times the exposure time in hours divided by the DAC. So this person might be exposed to half of the DAC for 2 hours. That would be 1 DAC hour. Might be exposed to twice the DAC. The concentration divided by DAC might be twice as much. And it might be exposed for 4 hours, and so that would be 8 DAC hours. So that dose is the DAC hours. So once we calculate the DAC hours, then the dose is equal to the DAC hours times the limit that applies divided by 2,000. So if we're talking about a stochastic limit that applies to the whole body, then we take our DAC hours times 5 rem divided by 2,000. If we have the doses to an organ, then we take our DAC hours times 50 rem divided by 2,000. So that's how we can use DAC hours to calculate our doses for the year. Now, when we have airborne activity, and since we're talking about DAC hours, talking about airborne respiratory pathway, then we have to consider the lung clearance class of the particular nuclide. So as you can see here in this example for strontium 90, there are two different clearance classes here. They tell me go see strontium 89 and 80, strontium 80, and so that's because they don't want to repeat this in every, let me find it, they don't want to repeat this in every situation, so they tell you to go to the original, to the first. So this, well, let's go to strontium 90. Let's go to S, strontium 90, and it tells me C, strontium 80, and that's because strontium 80 is the first entry for strontium. So in that first entry, they tell you what classes of material, what chemical forms are class D, what chemical forms are class Y. And so in the case of strontium 90, it's all soluble forms except for this tritiated version. And for class Y, it's all compounds include plus this one. Those are the clearance rates for these particular compounds. We could pick another example. Let's pick uranium. It'll be in the first one, so I pick uranium-230. It tells me that class are all these compounds, uranium hexafluoride and other gases. The W compounds are these particular soluble compounds, and uranium oxides are Y class because they're relatively insoluble. So that's how we find it. It's always in the first entry for a particular element, the first nuclide entry. So let's get rid of that. So we will find out what our classes are based on the chemical composition. And so so it has a fast clearing class and a slow clearing class. There is no W class for strontium. It's either soluble or it's not. So in the D clearance class, you can see that there is an organ limit, 30 microcuries, reaches non-stochastic limit for the bone surface. It also gives me the alley that would reach the committed effective dose. 40 microcuries would give me 5 rem to the whole body effective dose equivalent. But for class Y, there is no, it's not a bone seeker. For class Y compounds, the limitation is only for 40 microcuries. That's for the whole body for the effective dose equivalent. Okay. So depending on what chemical form you have, you might have different activities. Submersion doses. So some of these DACs that are prepared that calculate these are not done based on what organ is going to be taken up. So submersion for inert gases, noble gases, if a person's standing in a cloud of noble gas, they may breathe in that activity, but that's not they don't accumulate materials in their body. They breathe it in, they breathe it out. It's non-reactive. It's an inert gas. The dose due to a noble gas is due to the external cloud surrounding the person. So the activity that's in the air will shine on this person and deliver a dose to the person from external exposure. So the activity, the dose the person receives will be proportional to how much activity is in this cloud, what the concentration is in the cloud, and the amount of time. So it's also very similar to our situation for inhalation, that we can look at the concentration and the time exposure, and so we do DAC hours. So for noble gases, for inert gases, there are a class of compounds class of exposures that are called submersion doses. The dose is due to external exposure, and there is no intake, so there won't be an alley, but there is a concentration limit that contributes to the external exposure. That concentration is in DAC hours. The concentration is in DACs. The exposure is in DAC hours. And again, the effective dose equivalent from exposure to inert gases is the DAC hours times 5 rem divided by 2,000 DAC hours. Okay. Now, in occupational dosimetry, it's important that the dose standard applies to the entire dose a person receives. So that 5,000 millirem or 5 rem for the whole body includes both external exposure and committed effective dose equivalent from internal nuclides. So they both need to be added to be able to compare to the limit. So we get our reported external dose. Last time we talked about dosimeters, monitors that are worn. They might be TLDs. They might be luminescent dosimeters. But we have that dose that's been reported by our dosimetry processor, plus whatever the doses are, the stochastic doses, due to all the intakes that we have. That once we add up all these factors, that total exposure, must be less than the 5 rem. Now, for organ doses, we have the committed effective dose equivalent, committed dose to the organ. I'm going to fix that. I'll fix this as well. This should not be the EDE. This should be the committed dose of the organ. So we have the committed dose of the organ from an intake. The individual organs, even they are also receiving the external exposure, just like the whole body receives it. But as the whole body receives it, the individual organ receives it. So that we have the dose due to the internal activity. We also have to add our external dose. That's also contributing to the total dose for the organ. So that has to be compared to the annual limit of 50 rem. Now, this has described the NRC regulations, 10 CFR Part 20. The Department of Energy also has standards that apply to their facilities, and they have similar tables. In a way, they're similar. They have 10 CFR Title 10, Code of Federal Regulations, Part 835, has the standards for exposure for DOE facilities. Appendix A has the DACs for intake of radioactive material. They don't have alleys in the DOC regulations. They only have the DACs. And so you have to calculate what the dose is in the method we showed you for DACs. And 10 CFR 835 Appendix C has DACs for submersion doses from those inert gases. So the DAC hours method is used to calculate this. The DACs are based on the WR and WT values in a later method, ICRP 60. We talked about that before, that they added more tissue weighting factors and changed the radiation weighting factors instead of Q values in ICRP 60. Those are the basis for NRC regulations. And so that's why the numbers are different in DOE versus NRC. I'll give you a link here to the lung clearance classes have different names as well. That's because of guidance. It's fast, medium, and slow instead of daily, weekly, and yearly. And I give you a link to the table that's provided. Here is the table, an example of the table. And so we have, remember we said for strontium 90, there's only fast and slow. There was no medium. It's either soluble or it's not. Fast is the soluble relative, something similar to the D class in the NRC regulations. The slow is something similar to the Y class. Now, this, as a result, the different classes tell us, on the right hand column, it reports to us what organs or tissues are the basis for these standards, these DACs. In the F class, it's bone surface. That's the same as we saw in the NRC rules. For the slow or the Y class, it's stochastic limit, the effective dose equivalent limit. That's the same as we saw in the NRC case. Okay. And now I'm going to do an example calculation to show you how we assess dose. So the example we have is a work process generates airborne plutonium oxide. Air samples reveal that the activity consists of plutonium-239. That's the isotope involved. And the AMAD, the aerodynamic diameter, is 1 micron. That tells us how deeply the materials go into the body. So the measured concentration from air sampling is 1 × 10⁻⁹ microcuries per milliliter. This is another typo. I'll correct. It's 1.0 × 10⁻⁹ microcuries per milliliter. Worker must be in this environment for 2 hours to complete some task. What are the organ dose and the committed effective dose equivalent resulting from this workplace exposure? So we go to 10 CFR Part 20 to our table. Now, when we look at plutonium-239, it tells us C plutonium-234 for the classes. Plutonium-234 tells me that W classes is everything except plutonium oxide. Y class is plutonium oxide. In our problem, we're looking for plutonium oxide. It's Y class. It's insoluble. It doesn't clear the lungs. And we know that for Y class materials, the DAC is 7 × 10⁻12 microcuries per milliliter. So we have our concentration divided by the DAC times 2 hours. We do this calculation, we find out we have 286 DAC hours to the bone surface, because that's what L is for. So what is the dose? Well, we take our 286 DAC hours, and it's 50 rem for 2,000 DAC hours. And so if we multiply 286 times 50 divided by 2,000, we get 7 rem. Okay. Now, if we need to calculate the stochastic limit, in this case, we notice that the alley for the stochastic limit is equal to the alley for the organ limit. So this concentration, the same concentration, 2 × 10⁻², or excuse me, that same activity will give us 5 rem. So because of that, we can just apply our DAC hour calculation because of the same standards. Again, we don't need to make any adjustments. We can just take our DAC hours, and this exposure, the exposure we receive at 7 × 10⁻12 microcuries per ml will, in addition to give us 50 rem to the bone surface, it would also give us 5 rem to the committed effective dose equivalent. So for the same number of DAC hours, we get 5 rem for 2,000 hour exposures, or DAC hours. So the 286 times 5 rem divided by 2,000 will give us 0.7 rem as the committed effective dose equivalent. Okay. Now we're going to do an example using the NRC regulations. Plutonium oxide is insoluble. It's S class, so we're going to use the number for S class, 7 × 10⁻11 microcuries per milliliter. Do the same kind of a calculation. What is our DAC, our concentration divided by the DAC times the hours of exposure gives us 33 DAC hours. So the numbers are a little different, and so the DAC hours are a little bit different. Notice that the activity is now much higher activity than it was before. Here the dose was the DAC was 7 × 10⁻12. Now it's 6 × 10⁻11, resulting from different weighting factors used in this calculation compared to the other. So the dose of the bone surface, we're going to take our 286 DAC hours that we calculated. It's not 286. So what's the calculation for this? I didn't calculate it right. So we have 33 DAC hours times 50 rem. I'll get a calculator out. We have, let's say, 33 DAC hours. 33 DAC hours divided by 6 times 10 to the minus 11. So yes, I did calculate this. Oh, it is 33 DAC hours, not 286. So this should be 33 DAC hours instead of 286. I'll correct that. So 33 DAC hours times 50 rem divided by 2,000 DAC hours to reach 50 rem gives us a dose of 0.8 hours. I just didn't type that correctly. I used the wrong number. 33 DAC hours. So that's how this calculation would be done. And so you can see that it's a much lower dose because the DAC is much higher in the, higher in the DOE calculations than it is in the NRC calculations. I do want to say that there's, in addition to doing air sampling and calculating dose based on DAC hours, there is also monitoring. Now, for the radiation, external radiation last time, we talked about wearing film badges as a way to monitor exposure. We can monitor internal exposure as well. And there are two ways this is done. One is by direct measurement of the radiation that's in the body through some whole body counting or lung counting or some other technique where we use radiation detectors to quantify the amount of activity in the body. And that's one way we monitor for internal exposures. Another is we can monitor, take 24-hour samples of urine or feces, determine the amount of activity, the concentration of activity in the urine or feces, and this can also be used to infer the intake of radioactive material. So the way it works, we study this technique in more detail in the course on radiation dosimetry. I'm just going to mention it here. The process by which one does this analysis is one either takes the whole body count or the lung count or whatever, the measurement in vivo of the activity, or they measure the activity that's excreted in a 24-hour period. And then they use an intake retention function. Just like we have tables that tell us what the dose is given an intake, we have tables that exist that tell us after 24 hours how much of the material would be retained in the body, after 24 hours how much material would be excreted in the following 24-hour period. And so we use these tables that are intake retention functions that tell us what fraction remains in the body or is excreted from the body later on. Use that to infer how much activity was present at the beginning. So if we know that it's been a week since this person did their work activity, and now we know they have a certain number of mercuries in their body, we can use these tables to tell how much activity they had in the beginning when they were first exposed. And then we use that initial intake. Here's the process that we use. We measure the current activity. We use the IRS to infer what the original intake was. And then we use that original intake with the alley to determine what the dose is. So it's a indirect process. It requires calculations going back to whenever the intake occurred, and then use the alley tables to determine what their dose is at the present time. So I think that's everything we have to talk about today. I appreciate your attention. I appreciate your attention with this lecture, and I look forward to working with you as we continue on in the semester.